Thank you for that introduction. Oh, that was right. I was going to say I'm a PhD student at Maryland. In the last year, I've been doing research also with Arthur, a startup in New York that John Dickerson is the chief scientist at. And the work that I'm going to talk about today was done while I was there in collaboration with some wonderful people at that company. So today I'm going to talk to you about reckoning with the disagreement problem. This is a paper we have under review right now, and it's a response of sorts to a paper from your group. So I'm excited to get to tell you about all the stuff we've been up to. We'll break this talk up into a few sections and subsections. I'll start by going over the disagreement problem. So again, I know I'm speaking to some of the authors of that paper, but I think for the talk to be self-sufficient and contained, it's worthwhile to go over those details. Then we'll get into our main contribution in our paper, which is called PEAR, a post hoc explanation agreement regularizer. So this is a loss term that we add to training networks. And after introducing what that regularizer looks like and how it works, we can go through a few experiments. These are all sort of structured as hypothesis experiment results, and that'll include looking at whether or not PEAR improves consensus, the giveaways that it does. We'll look at consistency at what cost. So if your explainers do give you consistent explanations, does that cost you anything? Mostly we look at that in terms of accuracy. We can ask the question, are these explanations still valuable? And when we get into the details, that question is really quite a large one. I think measuring the value of explanations is really hard. And lastly, we'll talk about linearity and consensus and how those two play together. Like I said, I did this work at Arthur. So my collaborators were Max, Karthik, Keegan, and John. And I just want to note at this point, you should interrupt me with any questions or comments. I don't mind being corrected about the disagreement problem. If I say something that warrants more detail or subtlety, please let me know. But also stop me with any questions you have along the way about anything. I think that's the best way for this to be exciting and productive. Okay, so let's start with what the disagreement problem is. And again, I'm aware that I'm going to describe this to people who coined the term. So call me out if I get something wrong. The idea is that you have post hoc explainers. They look at particular input-output pairs and a fixed model, and they try to rank the input features in their importance. There's a whole family of these. So in a lot of my examples, we'll just talk about explanation A and explanation B. Those will always come from the same data point and the same model, but they're two different explainers. A favorite choice is to talk about Lime and Shap as two representative examples, and we'll get into the whole family of options in a minute. But the idea is that you have some input features. In this case, we have 5, just as an example, and we ask an explainer, how important are all of these, and they output some scores. Those scores are numbers. I guess they're not necessarily floating point numbers, but you can think of them as scores that don't really have units, and that's part of what makes this whole problem complicated. And so we can compare 2 of them by looking at those raw scores. They can often be positive or negative, and that's one way they might disagree. But like I said, they don't have units. So although my example here, all the numbers are sort of on the same scale, that's not even a requirement. You might have an explanation C where the scores are in the hundreds or thousands or 0.0001. So comparing these things, we don't always look at the absolute numbers. We can also look at the relative scores. We can rank these things by the highest score, the highest magnitude score. And we're going to get into the subtleties of when and why you would use any of those various tools. But the main point of the observation that we have a disagreement problem, and again, that's in this paper titled The Disagreement Problem in Explainable Machine Learning, is that for a single input and 2 different post hoc explainers, you're going to get different feature attribution scores. And that's a problem. That makes it really hard to know what to do with the feature attribution scores. If you're a data scientist in the field and you are trying to understand which feature is most important, you may be confused if 2 of your favorite tools are disagreeing about that question. So it's an important problem to analyze and to study, and there might be lots of ways to approach that. We're going to spend most of the talk on how to possibly train models to get away from this problem, and we'll get into that in a minute. This is a visualization of the same type of disagreement, and I didn't come up with this visualization tool. This was also developed in the disagreement paper. Although I did make this one with a model that we trained. So we trained this on a California housing data set, and we're measuring agreement here with rank correlation. We're going to talk soon about exactly all the metrics, but the idea is this is just looking at how correlated the ranks are in these explanations. And again, we have this grid where we're comparing each of 6 explainers against each of the other 6. So just to highlight something, this is symmetric. I guess you could say there's a little redundancy here, right? Lime versus Shap is the same as Shap versus Lime. And you'll notice along the diagonal, you get perfect ones. So that's the highest score you can get here on a correlation metric. And of course, Lime and Lime are perfectly correlated. So that meets our expectations. What's maybe notable is that not everything agrees, right? So in particular, if you look at the 3rd row down, grad, and the 4th column in from the left, grad times input, that correlation score is pretty low. It's not even the lowest here. It's just one that I picked to highlight. And those 2 things don't seem to agree. So maybe that's part of the problem. This in fact gets worse. So we can look at a different data set and a different metric. And again, I will go into what all the metrics are in a moment, but this is on electricity data. This is a classification model. And if we compare these explanations with sign agreement, so of the important features, how many have the same sign? Remember, those feature attribution scores can be positive or negative. And what that means depends a little bit on the explainer, which is why the sign is not always something we're looking at. But this is even worse, right? There's even more pale squares. You have a less concentration of red. And then, finally, we can pick an example where it's really bad on this particular metric and this particular data set. There's very little agreement. So this problem is complex, right? What I'm trying to point out to you in this slide is that there are a lot of layers here. Depending on how you want to measure agreement, you might get different numbers. Depending on which data sets you're looking at, this may or may not be as big of a problem. But when it is a problem, it can be very stark. And the other conclusion here, which I've alluded to now, but we'll just say really explicitly, is that we have a lot of metrics. We're looking at California housing with rank correlation, or electricity data and sign agreement, or bank marketing data. And these things are lots of ways to measure them, and they all have a little bit of an issue. So we really have kind of a large scope. And I think that point was made really well in the paper. Again, these are not findings of mine. So far, I'm summarizing the state of the field when we arrived. So this disagreement paper points out that this is, maybe we should say, pervasive, right? And again, in that original paper, there were several data modalities, tabular data and vision data. And I think there was some experiments on language data. And we have this sort of big issue. And even within that disagreement problem, we have an issue of how to discuss it, how to measure it, because of all of these metrics. So let's talk about what these metrics are, because we're going to use these names. We're going to throw these words around a lot in the next little bit. And it's important to have an idea of what's going on. So again, this slide is not my own work. These are metrics that are defined in that paper. They actually have really beautiful and rigorous formulas in set notation. They have to do with overlapping sets. I'm not going to put those formulas on the slides. And that's deliberate, because I think that they all reflect some intuitive question that a data scientist has when they look at explanations. So we're going to really think of these from their intuitive side. And if you're interested in those details, they're all in both the original paper and they're written in the appendix of our paper for reference. But for today, we're going to just think of these as 6 different choices of measurement, and I'll tell you what they mean sort of intuitively. So before we pick a specific one, we have a light purple box up here with top K metrics, and the bottom darker section is features of interest. In the top K metrics, these are all asking questions about which features are most important. So K here is a variable, and it's another one of the parameters that's sort of complicated for us in the research space to set and dictate and say is important in practice. A data scientist who's actually dealing with a data set with a lot of features might have a top K that's large. Someone who's dealing with a very small feature set might be picking a different one. So that is a choice in how you measure agreement and disagreement. For the purposes of this slideshow, we're going to just always say it's 5, because it'll just make the conversation a little bit easier. Okay, so just as an example, we're always asking about the top 5 features. So feature agreement is just asking the question, I have 2 explainers, here's a data point and a model that are fixed, and of the top 5 features that each gives me, what's the overlap? Okay, so maybe Lime tells you that features 1, 3, 5, and 9, and 12 are the most important, and SHAP gives you a different set of features that are most important, and we want to compare them. So this ranges on a scale from 0 to 1. We just normalize that, so we're asking about a portion of them that it agrees with, and we're not careful in this particular metric about whether it is the most important or the second most important, just if it's in that group of top 5. Okay, do they agree? So rank agreement is a little bit stricter. Rank agreement says of that group that are in the top 5, how many get the same rank? So do Lime and SHAP ascribe feature 2 as the 4th most important, or do they disagree about where it falls in that ranking of the top 5? So this is a stricter metric, and it takes into account rank, which is something that, again, in the field, a data scientist might care about. So we're going to try to not tell a data scientist what they care about, but give them the tools to ask whichever questions that they need to ask. And if they care about rank, they're going to look at this particular metric. Sign agreement is another variation of feature agreement where we ask of those top 5, how many were given the same sign. So rank didn't look at the absolute scores that come out, right? If Lime gives you a feature importance score for the first feature of 2.5, and again, these things are kind of unitless, so they're difficult to compare. Rank agreement doesn't care what that number is, it just compares it to the other feature importance scores. Sign agreement still doesn't care about the absolute value of that number, but we are now looking at the sign. And for different explainers, the sign the sign might mean something different. So we do have disagreement in that sign as well. Signed rank agreement is now a combination of these things. How many in the top 5 have the same rank and the same sign? Okay, so the top K metrics are all asking questions like that. These other 2, rank correlation and pairwise rank correlation, are looking at features of interest. In other words, tell me something about the high features and the low features. So I'm not going to set a K here, but just if you look at my feature ranks, are they correlated? Do similar features get similarly high or similarly low scores across 2 explainers? So these are 2 different flavors, and within those flavors, we have lots of choices. This is like a whole menu of how to ask the question, do things agree, right? So I'm taking so much time for this because I want to drive home the point that there are a lot of ways to measure, and they may not all agree. Oh, I didn't give you the details about pairwise rank correlation. Sorry, pairwise rank correlation asks for specific pairs, which is higher. So we're no longer looking at the rank of a feature within the whole feature set, but if you just pull the 4th feature and the 8th feature, you ask the question, which one got the higher rank, right? Okay, so there are a lot of different ways to measure. We should expect that maybe when one metric looks good, another one doesn't look good because they are different. And this is important for us because we're gonna look at a type of generalization that includes moving from one of these metrics to the other. So what I mean by that is typically you have some training data, and what we call generalization is how well you perform on unseen test data, whatever your task is. We're going to add a couple of axes of generalization in this talk. So in addition to asking how well things work, both accuracy and agreement metrics, how well they work on training data and then unseen test data, we're also going to ask, do we still have agreement when we look at a different metric? That's like a slightly different type of generalization. We can similarly ask, do we still have agreement if we change out the pair of explainers? So that detail is a little bit hard to describe until we get into what the pair loss term looks like. And I'll come back to that. But that's why it's important to see how wide this field is, right? All of these different ways to measure. Okay, and I'm going to show you now a couple of examples of how subtle these things are. So before I reveal my answer about whether these 2 explanations agree, look at them for a second and decide for yourself if you think these are generally in agreement or not in agreement. And I'll just point out, so that you don't have to look for the tricks. The blue features 1, 2, and 3, Oh, it looks like we have 6 features and only 5 labels on the left. I'll have to fix that. But the top 3 features in blue are all similarly ordered, and the bottom red features are also similarly ordered across these 2 explanations. But the absolute values of their scores are different. Okay. So by eye, these look pretty similar, right? And if we look at a correlation of the actual scores, so we leave the minus signs where they are, then basically these are extremely similar vectors. So we can measure that correlation, and this is slightly different than the rank correlation we just talked about. We can measure that correlation with Pearson. That's just from statistics, a correlation coefficient. And we're going to see that this vector 0.65, 0.64, 0.63 up on the left and 0.62, sorry, negative 0.62 up on the right, that those are pretty well correlated with Pearson. Now, they're not correlated if we ask about their rank first. So we're going to take their rank by doing the absolute value of these scores, in which case on the left, that bottom feature, which is really the 6th, but looks a lot like feature 5 on this slide, that's really the highest magnitude feature on the left, but the top one on the right is the highest magnitude. Okay, so Pearson says these are almost perfectly correlated, and it is actually perfect at 2 decimal places in my computation. Spearman, which is a different correlation, that's a metric that looks, that actually is what we call rank correlation on the previous slide. Those could have been named the same thing. That says they're actually more negatively correlated, and they're even not very negatively correlated, right? So Spearman is, both of these metrics go from -1 to 1, and they're giving you really different answers. Okay, we can actually look at this again with a different explanation. We can find a time when the ranks are perfectly correlated, but the actual values are not. So there's a huge amount of subtlety here, and it's really difficult to look at 2 explanations and decide if they're a good match or not. These are our examples that we concocted to show how complicated these are. These don't come from a particular problem or model, but if you are looking for human intuition about agreement, even that is complicated, right? Does this bottom one look better or worse than the top one? It's not so clear. Okay, so that's just a little bit more example-driven discussion about why disagreement is hard to measure, why we want all of these metrics, and it's a little foreshadowing. We're going to use both the Pearson and both the Pearson and the Spearman, correlation coefficients in our loss term. So that's going to come up again. Okay, that's everything that I have to say about the disagreement problem as background. So we're going to sort of shift gears now and talk specifically about this PEAR loss term, post hoc explanation agreement regularizer. So this is a secondary loss term that we add to training. And the goal is to find models that have some consistency across explainers. Okay. That's we're leaning on some existing work of adversarial training or training with a certain fairness loss. Multi-objective neural network training is not something that's so new. And one nice thing from those spaces that we can sort of expect in our space is there tends to be a trade-off with accuracy and whatever your secondary goal is. So we're going to look at that in a few minutes. But the real question we want to ask is, does this even work, right? So can we train models to be accurate and show agreement among explainers? Okay. If the background from this talk was either too long or too boring, and you're tuning back in now, that's fine with me. And this is really the question for the rest of the talk, right? Can we train these models to be accurate and show agreement among explainers? To our knowledge, we're the first or among the first to ask this question and formulate a loss term and do these experiments to see if we can find neural networks that don't have a disagreement problem. Okay. So one last visualization of what's happening. Again, if you are not in this space, I think this is illuminating. If you are, maybe this just serves to show what we're going to do and the data types that we're going to deal with. So in our experiments, all the data is tabular data. What that means is you have some big spreadsheet. Maybe the columns are age, gender, income, debt, open cards, how many open credit cards you have. We're going to take a row of that data corresponding to one customer that your bank might have and ask our model, should this person get a credit card, right? It's an application model. So we put in their data and the model says, you don't get a card, right? The application is rejected. Now the client wants to know like why, what went wrong, but our model is a black box or a bright purple box, but you can't see inside of it. We don't know what's going on. So we need an explainer. Maybe we should have started with this, but so this is what the explanations do, right? They pick some features and they say, your income is $110,000 a year, and that's good, that's helping you, but you have $20,000 in debt, and that's hurting you in this case. And if you're data scientist, or maybe even one step removed, if you're a loan officer or credit card applicant reviewer at a bank, you now have some information that you can pass on to your client. That's really helpful. Okay. The problem is that if you ask explanation 2 or explanation 3 or explanation 4 from these different explainers, what's helpful and what's hurtful in this person's application, that there's a lot of variety, right? So maybe the age is what helps and the open cards are hurting you. And this is really hard because they're all doing something valid, right? Each of these explainers comes from a paper where the authors did something rigorous and showed with empirical results and maybe some theory that these explanations tell you something. But if they give you different conclusions, then your loan officer or even your data scientist might be confused as to what the model's really looking at. And so what we're aiming to do with PEAR is to smash all of these into agreement. We want them to say the same features are good and the same features are bad. We don't have ground truth for this. So this is something that we could talk about briefly now and comes up again much later, but it's very hard to look at an explanation and say it's right or wrong because we don't know what the model is doing. So someone with a lot of experience in a particular field, let's say in loan or credit card applications, might come and look at this and say, the thing you should say is helpful is your income, and the thing you should say is hurtful is your debt. But that person's explanation for the way they would make that decision doesn't have to match up with what our explainers say our model does, because we're using the model specifically so that we're not relying on some human process, right? The reason to use a machine learning model to do this application problem, to solve this application problem, is to do better, right? To get superhuman performance. So maybe those aren't the right features to look at. And that makes it really hard, even with expert consultation, to know which features are really important. And that's just a little motivation. That's why agreement would be so great. If every explainer in your toolkit gave you the same explanation, you might have a lot of confidence that that is really what your model is sensitive to. So that's why we're after agreement. I think that there is a little bit of an open question about whether post hoc explainers are really giving us a view into what the model's doing in a way that is useful, or how meaningful those explanations are is sort of remains to be seen because of this problem that we don't have ground truth. But as far as this project goes, we're going to say that if they all said the same thing, we would be a little more comfortable using that information in practice. Okay, so here's our loss. And maybe the comically large parentheses on the screen will make the math not so hard to read. But we have a lambda weight, so that's going to control the force of whatever's in these parentheses, and we're going to add the Spearman correlation and the Pearson correlation in a convex combination controlled by mu, and that is our PEAR loss term. So Spearman and Pearson are written out there. That math is correct and important, but I'm not going to read it to you. I think that knowing that it's a convex combination of these two correlation terms is enough for this talk. Of course, those details are on this slide and in the paper if you're interested. So our whole loss, our big capital L now, which we're going to do gradient descent on, that's how we're going to train our models, is itself a convex combination of your task loss, that little scripty L. And so for classification, that'll be cross entropy. And then lambda times this PEAR loss term, which we've written out symbolically without the really large parentheses here. And so that's mu times S, which is the Spearman function of two explanations, plus 1 minus mu times P, or the Pearson correlation of this very same two explanations. It's at this point that I would say we have lots of convex combinations and we're introducing new hyperparameters. So lambda and mu are two things that we do experiment with quite a bit in the paper. And as that comes up in the next few slides, I'll go back I'll try to make clear which of those we're tuning. The other really important piece of information here is what E1 and E2 are, okay? We're gonna pick two explainers to train with. For the purposes of this talk, we're actually, all of our experiments do the same pair, so we can really nail that down. We can say E1 is gradients. Sometimes that's called vanilla gradients or saliency maps. And that is just asking the network what the gradient of the loss with respect to each input feature is. And we're actually going to take the absolute value of that. Okay, so gradients gives you negative scores until you do that absolute value. And E2 is integrated gradients, which on my slides is referred to as intgrad a lot. And that explainer, a high-level quick summary of that is you're looking at basically the gradient, but at a whole bunch of points in input space as you move from some baseline over to the point of interest, i.e. your input, the X that you actually care about, and you integrate the gradients along that path. These are two explainers that don't typically agree, but we are going to, on each forward pass, ask those explainers for their feature attribution scores on the input point X. And again, E1 and E2 are functions of X and Y because they need the label to know they're actually functions of Y hat. This is, I'll show you on the next slide. I have that a little more precisely, but they need to know what the model's output was to compute gradients. And we're going to get those explainers, those explanations, and we're going to compute the Spearman correlation. So that's the correlation of their ranks, and the Pearson correlation, which is just the correlation of their actual output values. And we do both of these mostly motivated by our observation a few slides ago, that you can have examples that look good to us, to our human eyes, but Pearson says they're good or Spearman says they're good and the other says they're bad. So we actually want both in line. A more quantitative answer to why we have two terms is that if you just ask for Pearson correlation of the actual scores themselves, not the ranks, we find that the loss is very happy, the loss gets very low if the feature attribution scores get small magnitude, right? So it's okay to just say the actual score that you output is very, very close to 0, and then the order of them seems to matter less as far as the loss term goes. However, if you only ask for Spearman, you lose all of your access to negative signs, right? If you rank these things with their absolute value in your loss, you don't keep track of sign agreement or sign rank agreement, and those are things we're after. So to get all of those 6 metrics that we talked about to show agreement, we have some convex combination of these two loss terms. So here's a little graphical description of what's going on, and this is where I said it really takes in Y hat. This is not a computation graph that I would say is a reference for how gradients flow, although it's sort of inspired by that type of diagram. But basically, this is how information moves through the pipeline over to our loss function, right? Your ground truth labels Y are really important in computing your task loss. Cross entropy needs access to that. Your model inputs have to go through your model and through the explainers to show up in your consensus loss. So if you don't like symbols, if you're into images, this sort of captures all the information on the previous slide, right? Are there any questions about the loss before I go on? Okay, great. That's wonderful.
So for the gradient-based methods, like this optimization is on, I'm assuming it's you're calling it like a new explanation method in some sense, or is it an improvement over, like, let's say for gradient-based methods, there is no, for Lime, I can see that you need the model outputs and down labels to kind of like the local model, but for gradient-based method, how is it?
So the gradient method also, like just vanilla gradients, needs a model output to look at, because you want to take the gradient of a scalar output. So not all the logits, but like the probability that you fall into a specific class. And the way we do that is by looking at the class that the model would have put it in. So we actually need to know that, like, argmax. That information is actually packed into the logits, right? You don't have to literally compute the argmax before you pass that information. That's an implementation question. But that's why that goes in there for the gradient-based stuff. Yeah, so I would say we're not inventing new explainers. We do have differentiable versions, which for vanilla gradients, for example, is not so complicated. There's no problem finding the gradient of the gradient with respect to the input, right? These are things that PyTorch can do for us. But that was a technical hurdle in this project, is to build a pipeline where you can get explanations and then back propagate through this whole tree. Yeah, did that answer your question?
Yeah. So one more question, actually, following up on that. So I guess then your answer is also probably suggesting that you almost treat E1 and E2 like inputs that would be plugged into your objective. So it's essentially like there are, I guess, two steps. One is you're trying to come up with a model. During the process, you'll sort of call the explainers, get explanations, and plug it in. Is that understanding correct?
Yeah, yeah. E1 and E2 don't have trainable parameters. So like as layers, if you want to think about them that way, they won't move while you're training, but you need to compute them in order to compute your loss before you differentiate. So yeah, they're inputs to our loss. Yeah. Okay.
Sorry, did you say that you were able to differentiate through other explanation methods?
Yeah, so we tried this. Of the six, I think we have 6 explanation methods. Of the 6 explanation methods, Lime and Shap are the hardest to differentiate through, but we have differentiable versions. They just take absurd amounts of time, and we sort of, this is a design choice, but we chose to leave those as evaluation explainers instead of using them in the training loop, precisely because they're the most popular. And if you're a data scientist, what you're going to care about is Lime and Shap. And by leaving them out of the training loop, we're able to really like study this generalization from trying to get gradients and integrated gradients to agree, and then look at whether Lime and Shap agree more. So yes, we can differentiate through them. It's very slow.
Thank you.
Yeah. Okay. So we're gonna ask this question now, which hopefully everybody's excited that the answer is yes, but can we improve consensus? And we're gonna do this section of the talk for the next few slides. I'm gonna present to you a hypothesis, and then we'll talk about an experiment, and I'll show you the results. So the hypothesis here is that we can increase consensus by deliberately training for post hoc explainer agreement, right? The sort of the hypothesis of the whole paper. The idea to try this comes from the hope that putting this loss term into our pipeline yields good results, okay? So we can do this by turning that lambda value up from 0 to non-zero. So I'll just remind you, lambda is the parameter that controls your task loss and your pair loss term. Okay, so we have a convex combination of those controlled by lambda, and at lambda equals 0, you are only training on your task loss. That's like naturally training is sometimes what we call that, just cross entropy. If you turned lambda up to 1, which I'm not going to show you results from because you get very weird things happen, but that would be like, you don't care about accuracy, you just want all the explanations to be the same. Okay, and we're not going to talk about that extreme today, but if you're interested in that, we can visit that at the end for sure. And here's a really easy way to check. We take a baseline model, which again, that's lambda 0. We train that on the electricity data set. And then we look at the rank correlation agreement between Shap and Lime and Grad and Lime, right? All our explainers in Lime. So our y-axis here is agreement with Lime. There are no numbers here because rank correlation is between 0 and 1. But higher is better is really like the important part, right? We're just showing that we can boost this. So ours is the same model, but that lambda value was turned up to 0.5. And the 2 explainers in our loss, which are also hyperparameters now, is like I said, is grad and integrated gradients. And we see that by training to make grad and integrated gradients agree, Shap and Lime get more agreement, and grad and Lime get more agreement. In fact, every single one agrees with Lime more than it used to. So this is exciting, right? This tells us that our regularizer is doing something good. We can visit a familiar visualization technique and look at these red grids. So as I'm sure happened to the authors of the disagreement paper, we ended up inundated with red grid files, hundreds of red grid files. And it was really fun to see that as lambda goes up, so again, on the left, lambda 0, on the right, lambda 0.5. As you turn lambda up, you get more red, right? You get more concentration or saturation. And that's a good sign. That's like quickly with your eyes, you can see there's more agreement. Feel free to go look at the specific numbers, but the point of this visualization is to see this jarring contrast. So pair leads to more agreement, right? That's great. It leaves us with some questions. What happened to the model, right? We obviously have a different model here because the way that these explanations are computed is not different. The data is not different. So our model is doing something different, and I haven't addressed accuracy or explanation quality. And so the rest of these sort of probes, hypotheses, and experiments we're going to look at now are sort of like, okay, we can get agreement. What happened to get there? What changed? What did we give up? Does that sound good? So the first thing we'll ask is at what cost? And here I specifically mean in terms of accuracy, right? And I'm going to hypothesize that we're increasing consensus with an acceptable drop in accuracy. If you are a technically minded person, you might be upset that my hypothesis has the word acceptable in it, because that has a lot of flexibility and I might have a lot of latitude to say, yay, we proved our hypothesis. But I'll tell you what we mean by acceptable here. If you are a data scientist in the field and you have a really strong need for agreement or for explainability, maybe at large, there are choices you can make to avoid the disagreement problem that are earlier in your data pipeline than where we're inserting PEAR. Okay, so one thing you might do is you might say, I need to understand my model. I can't deal with neural networks. And you go train a decision tree or a linear model. Linear models are considered to not have disagreement. That doesn't mean that if you compute it, it's literally, you get agreement of 1 every time because numerical models are numerical models, but we don't even really need the explainers, which is the point, right? If we're training a logistic regression model to do binary classification, you get a linear decision boundary, and that is explainable. We can go look at the weights of the model, and that tells you which features are being weighed, and it's not dependent on which data point you look at or which explainer you need, because you don't really need explainers. So what I mean by acceptable drop is that if you are someone who values explainability so much so that you would use a linear model instead, then you must be satisfied with the accuracy you get with a linear model, which again is lower than a neural network, right? Our neural networks are high performing models, okay? So we're going to compare the accuracy against this baseline of a linear model. And that's the dashed blue lines, these vertical lines. They're shaded to show plus and minus 1 standard error, just to point out that linear models have a pretty tight band. Yeah, is that a question?
Yeah, there is a question.
Yeah, can I have a question? Sorry. So, like, I was curious that, like, is it really true that, like, if you apply the various post hoc explanation method to logistic regression, you will have consensus among this method?
Okay, so depending on your implementation of these explainers, your consensus will be, it might not be perfectly 1 to floating point precision. It could even be as low as 0.8, 0.85 or 0.9 we found in some of our experiments. But that's a little bit of a failure of these explainers. So let me just tell you what I mean there. Lime is one version of Lime fits a linear model around the data point that you care about, right? That's how it works. And then the weights of those linear models are your feature attribution scores. If the model you are studying, if your actual pipeline has a model in it that you want to understand, if that model is linear, then a local approximation by another linear function ought to be the same model, but it won't always be, because Lime has some sampling and you have to fit things. And if you're looking at a data point that happens to be very far away from the decision boundary, then your sampling neighborhood might not have enough information. So Lime may not always recover exactly that linear model, but it should. And so if you go and compute your disagreement metrics with these explainers without taking care to treat the fact that what you're looking at is a linear model under the hood, you might get disagreement numbers that are in the 0.8, 0.9 range. But I'm going to argue that like conceptually, that's a failure of our implementations. That's not really because they disagree, right? This is a subtle point also. I will say that. If you
makes me wonder, like, whether it makes more sense to, like, in your consistency regularization, you only include those who agree with the linear model, nonlinear models, so that you rule out those, like, kind of bad explainers in your consistency. So, because, like, if you include everything in your consistency regularizer, it might be a little bit too demanding. Like, if you include all those bad explainers in your regularizers, that might be too demanding for the models.
Yeah.
Like, sorry.
It's a good question. Okay, so we only looked at regularizers that look at a pair of explainers. We didn't explore the possibility of having lots of explanation tools inside one explainer, one regularizer. But even so, the question of whether this loss is demanding or not is one that we sort of looked at the beginning of the project and felt a little like, let's try it and see what happens. So there's a little intuition that some of these things should be hard to align. And we find that our regularizer still can do it. So when we're worried about this being too demanding, I think the empirical results sort of speak for themselves. We can make these things agree, and we see agreement across these other explainers. So I don't have a satisfying answer for you to say like, oh, it should be easy to optimize this. Like this objective might be very wacky, might be super difficult, but it helps. And we have a couple hyperparameters that let you sort of scale how much force it has. And I think there's really more a practical conclusion here than there is a theoretical one. Although it brings up a lot of really good theoretical questions that I don't have such great answers for at the moment. Yeah. Okay, so actually that was a good question for these plots. What we see is that on the x-axis we have test accuracy, and on the y-axis we have pairwise rank agreement. So that's one of our agreement metrics. And again, that ranges from 0 to 1. I've zoomed in on the scale here because things are happening at kind of a sensitive scale. But our accuracies are always higher, right? All the colorful dots are always to the right of the blue dashed lines. So we're never getting close to the accuracy that a linear model would get, but we are getting a lot more agreement than we would get at our MLP baseline. So all these models are multi-layer perceptrons. That's also one of the future work directions, which we'll talk about later. And the baseline is where lambda is 0. Okay, so if there's no regularization, you just train for accuracy. On the bank marketing data, you get around 79% accuracy, and your pairwise rank agreement metric is 0.5-ish, 0.52. That's not a lot of agreement. Okay, Lyman Schaap disagree, you could even say. And then as you turn lambda up, you can move along this curve. I'm looking on the left from that pale dot to the red dot to the purple dot. You can move along this curve up, you lose a little bit of accuracy, but you gain a little bit of agreement. Now, there is a Pareto frontier in this space. I can't with any confidence tell you that's what we find with our model, right? There might be a lot of room for improvement, but we have this nice curve. And in fact, on the left, it's even convex. So there is some trade-off without really an optimal point. And this gives a lot of control to the data scientist who might need some agreement and be comfortable with some cost and accuracy without jumping all the way over to that blue dashed line where you're going to lose a lot of accuracy. So I think that it's fair to look at these plots and say, we do have a cost in accuracy, but it is acceptable. In other words, we still get more accuracy than somebody who needs explainability could get without this tool. Okay. And there's a whole variety of these plots in the paper, by the way, with different explainer pairs and different data sets. Again, Lyman Schaap is sort of, I think, the valuable one, not the most valuable. They're all important, but it's the one that if you query data scientists, they're using more often than anything else. I got that information from the disagreement paper. I have not conducted my own surveys, but they are popular, which might in part be because they are so easy to download and run, right? That's one big component here. Okay. So we can ask this other question: are explanations still valuable? And we talked briefly before about what it means for explanation to be valuable, and it's complicated. It's really, really hard to decide that an explanation is good or bad. So in our hypothesis here, we're going to say, and we're going to hope to disprove this, we're going to say the hypothesis is that we only get consensus trivially. In other words, we're getting feature attribution scores that are uninformative. So of course they agree, but we've really like damaged our ability to understand these models. And the way we're going to test this is a sort of roundabout method, right? We don't have ground truth for feature attribution. So we can't go look at the feature attribution scores on any given sample and say, well, now they're bad, because we don't really know what a good one is. But we're going to add junky features. So we have this whole table of data. We have all these columns that are really important, like income and debt and all these other things. And we're going to add a bunch of columns to the end of our table that are random. We're going to fill them with noise, which means we know for certain that they have no predictive power, okay? Our model should still fit all this data because the neural network can easily learn to ignore features that are not predictive. They're not hurting the problem, they're just uninformative. The question is, when we turn PEAR on, when we train with the regularizer, is our explanations gonna put importance? Are they going to ascribe high feature attribution to those junky features? Now, the reason that this test is sufficient for this hypothesis is that we've provided a free way, a really simple way to get agreement across explainers and to have accuracy that if that's what was going to happen, you'd think you would see that, right? It wouldn't be hard, you would think. Okay, what we find is that our explainers appropriately attribute near zero importance to these junky features, okay? And to give that a little more quantitatively, junk features are placed in the top 5 at most as often as models trained without PEAR. So we're not giving these junky features any feature attribution, which makes us feel like we are still getting informative explanations. And I say that all with the little caveat that it's hard to measure how informative an explanation is, but this is a way to say that it didn't take the free ride we offered it, okay? The last section of this series of experiments is about linearity. So like we were just discussing, a linear model is sort of considered to agree, right? It's considered interpretable or explainable or transparent, whichever word you like best. But it has weights that it ascribes to features, and there's nothing in it that should be too complicated to understand. So maybe if we get consensus, what happens is we're pushing our model to behave like a linear model. And this is also something that is a little nuanced to measure quantitatively. So we're going to do a qualitative and a quantitative analysis, okay? Our hypothesis here, as I just said, is that encouraging explanation consensus during training encourages linearity. And we can check this first with a visualization tool. So on the left, each of these panels is a plot of the level sets in the logit surface. So we're looking at the probability that the model ascribes to being in class 0 and how that changes as you move in input space. Now the O, the X, and the triangle are 3 real input points. They come from our test set. And the plane that we're plotting here is actually the plane that spans those 3 points. So we have no fancy projection here. We don't have any distance preserving metrics. These aren't t-SNE plots. This is an actual plane of input space. It doesn't necessarily include other points that are in our data set, but it is a plane that's spanned by real data. And as we move from point to point, we see that the confidence that you belong to a particular class changes. That's good, that's fine. When lambda is 0 and we train this thing naturally, we get very wacky contours in these level sets, right? And as we turn lambda up, as we use more of this regularizer, those lines are all straightening out a little bit. On the right, we have from an actually linear model, just as an example to see what happens. Okay, this is qualitative. Firstly, I'm not measuring how similar these curves are. I'm just asking you to look, but also I'm showing you just one slice of input space. Across other axes, we might get nonlinear behavior, but we did look at this for a wide sample. We looked at a lot of different sets of 3 input points and planes, and we do see this pretty consistent trend that on these planes, you get straighter and straighter level sets, okay? So this is a little qualitative understanding that we do get linearity by encouraging consensus. Now, I'll just say, we don't get perfect linearity. We know that from the accuracy measurement, right? We are more accurate than a linear model, and the linear models are easy to learn. Those are repetitive results, right? If you train a linear model on the same data set twice, you should get basically the same thing back. Okay, so before we get to the quantitative way to measure this, I'm just going to introduce a new hypothesis that we'll test, which is that linearity implies more explainer consistency. Maybe we've worked way too hard. Maybe if you could just encourage your boundaries to be more linear, you would get consistency, and you don't need this whole complicated pair loss term, right? That's what the last slide made me think when we looked at those results. We had a real moment of doubt, like, oh, is this more work than it's worth, right? Do we just need to find some way, and there are cheap ways, to ask our boundaries not to be so contorted? So one way to do that is with weight decay. So on the y-axis here, we have error of a linear fit. So lower means more linear. And on the x-axis, we have 2 different things. We have the lambda value on the left and the weight decay coefficient on the right. These curves share the same values on their y-axis. That's exactly the same y-axis. And you see they're pretty similar. So that model on the right, or that series of models on the right with different weight decay coefficients, all of those have lambda equals 0. And we can turn weight decay up. If you're interested, this weight decay is really large. That x-axis is actually a log scale. But you can turn weight decay way up, and you can fall down this linear fit in almost the same pattern that you do with lambda, and you get basically a similarly linear model. But we can go evaluate that model for consensus, and we see almost no change. It's near zero difference from the lambda equals 0 case with weight decay is 0.002. Weight decay coefficient of 0.0002, that leftmost point, is what we use by default in our code. So that's sort of the baseline. And turning weight decay up gives you more linearity, but it doesn't give you more consensus. So we're going to reject that hypothesis, right? We have one direction that it does look, and here this is quantitative. So this is the quantitative part of this. We do get a better linear fit, but we don't get more consensus if we do that a different way. This justifies using PEAR, and it sort of decouples linearity and explainability consensus. Even though those things sometimes look like they come together, there are ways to see one and not the other. Okay, in conclusion, and I know I'm almost out of time here, but we demonstrated that our loss term is effective. That's sort of the goal of a paper like this. Are you introducing the loss term? You should show that it does what you want to do. With any first attempt at a new objective, so with like the first adversarial training papers and the first fairness training papers, our results are modest. I don't think that you should look at these and feel like consensus is solved. We also have evidence that this can be tuned on a per use basis. I didn't actually speak about the mu hyperparameter that much, but we set mu equal to 0.75 in most of our experiments. It seems to be a good number across the board. In further experimentation, with each data set, with each metric, you might find a mu value that's better or worse. So there's a lot of control here that somebody might be able to take advantage of if this was to be used in the field. Which leads me to the last point, that this is not a how-to guide, right? We're not really telling anybody, do this thing and you will have explainer consensus. We're really just showing that there is control over the accuracy agreement trade-off, which is a trade-off that's made all the time in practice. Like I mentioned, there are fields where data scientists are not using neural networks because they need some transparency, which they get with linear models. So they have these extreme points of accuracy and agreement, and we're smoothing out to that transition. We're offering you a way to say, okay, maybe I turn lambda up a little bit and I can slide along that. And in a particular use case, a lot more control might be gained with domain-specific experimentation. So these are sort of the main takeaways, and I'll end with some future directions. Like I said, our loss term is defined generally for E1 and E2, whatever those explainers are, but most of our experiments have them set to vanilla gradients and integrated gradients. That isn't, that choice was made intuitively. We like the idea that if those two agree, everything else should, but you might get other behaviors with other pairs of explainers, and that's something worth looking into. There's also human evaluation, which was done in the disagreement paper. There's some nice surveys of data scientists. We don't know that data scientists would like this. We also need human evaluation for the quality of explanations. So my experiment there, the second or third to last with the junky features, is a little bit lacking. It doesn't quite tell you that the explanations are good. It just tells you they didn't take this cheap way to be bad. And human evaluation might be the right way to find a compelling result that the explanations are still informative and valuable. We could also look at other model architectures and sort of consumed in that as other data modalities. We studied tabular data and MLPs. People are using transformers on tabular data. Certainly people are using more complicated architectures with vision data. And I think that relates to the last slide. We're really showing a proof of concept here more than an in-depth like what to do in every scenario. So we didn't look at vision, but other architectures and other data modalities would be really interesting to look at. And then lastly, and this I don't have a particularly good vision for what it should be, but there might be more powerful consensus loss terms. So this is a first go at it. I would like to think it's a creative attempt at getting consensus through regularization, but we threw two correlation coefficients together, and maybe there's something more complex or maybe even more elegant or more subtle, maybe something more powerful that could be done. Like I said on the last slide, our results are fairly modest, which we feel is good for a first paper, but we're starting this sort of conversation of maybe we can train away the disagreement problem. Okay, are there any last questions?
Thanks so much, Avi. A couple of quick things. So I think I don't remember if we discussed this earlier, but did you guys also check what happens to the robustness of the models or like the fairness and so on, other properties?
We didn't look at that in the end. We had that idea that if you get straighter boundaries, one thing that might come of that is adversarial robustness, and we didn't look at that. Yeah, adversarial stuff with tabular data is a little more nuanced than with vision data, and so getting all of that done is maybe a project in its own right.
I think one question that I get when I was going through and I saw that different report is that, like, from a practitioner's point of view, I would be very careful in like injecting explanation in my training process that will be actually explaining that model. So, you know, like it's kind of like it would be hard to interpret the explanations that I would get for that model, because in some sense that was assisting the training. So, you know, there's this maybe a more, you know, it's just a little bit hard to convince that it should be part of like a training process, or should we keep it more on the evaluation front as to whether it's able to explain the model.
Yeah, I think that relates to this question of, are the explanations you get at the end of the day, are they still interesting? It's not I might also hesitate, in other words. It's hard to know that for sure. I think that one thing that's nice is that we see the accuracy is still there, and explainers other than the ones we use during training are also agreeing more. So if we don't train on Lyman Schaap, but Lyman Schaap tend to agree after the fact, I think that I also wouldn't recommend to a practitioner that this is done before further study, but I feel like from a scientific standpoint, there's reason to think that we are still getting good explanations, especially if you use a different explainer than the one you use during training, right? Maybe that concern is alleviated a little bit in that way.
So can I quickly touch upon like the premise of what we are doing here? And yeah, I'm just kind of going back and forth when I think about the premise of let's learn models that will ensure that explainers agree, right? So I kind of see your presentation and I feel like, yeah, we can control the accuracy drop from not being too extreme. But at the same time, this question keeps popping up in my mind that we all know that these explanation methods are somehow, you know, they're often criticized that they're sort of coming up with their own perspective of like, you know, here is a way to explain, right? So given that criticism or based condition on that criticism, what do you think about like the premise of this? Is it a good idea to sort of say, oh, let's now learn models which kind of equalize all of these? But I also think there is a counter example, which is if I just think of, say, something like gradients and smooth grad, right? So smooth grad is basically just like averaging out gradients. And if you are trying to keep or, you know, write down an objective or optimize an objective that's kind of equalizing smooth grad and gradients, I can see that you're essentially trying to improve some sort of smoothness of the models or like have similar gradients in any given, you know, epsilon ball or something in the feature space, right? So that I can see is like, you know, you have a very clear goal that you want to go in the direction of like a more smoother model when you do that. But when you add all these like Lyman Schaap, integrated gradients, everything into the mix, I'm kind of going back and forth on, is our premise that let's train a model that optimizes for agreement? Is that a good premise, or is that a good way to go about it?
Yeah, that's a great question. We actually started with some experiments with grad and smooth grad because we liked that you can really describe what the objective is, right? And we moved to integrated gradients because it's similar. You still have a gradient signal from different places in the input that you want to match locally. So there's a smoothness idea there. And it seemed to train a little bit better. But so yeah, so the the premise is complicated, and I think that in the paper we did our best, and maybe it could be even said better, but like whether you care about these explainers agreeing is dependent on whether or not you care about these explainers. And you're right, they get a lot of criticism. Some people think there's like no reason to look at them, or the fact that they disagree just serves as an example to show how ridiculous all of them are, or that they're all just slight variants. There's also an opinion that maybe they give you different answers because they're actually asking different questions, and that's fine. Like agreement across explainers is not that important. I think that these are really huge questions in the XAI space. And I don't think that we're really answering them. I think we're sort of sitting in a corner of the room where it's like, if you're going to use Shap and Lime all the time, you might want to try training to get two of these explainers that are gradient based to align, because if that gives you more consensus, but it doesn't change things that much, maybe that's fine for you if that's what you wanted. And I don't really have a good answer to the people who are wondering like whether we should care about this at all. It's a really hard, I think, question for basically everybody working in XAI, right? There are like a lot of XAI results that are sort of like, if you don't care about explainability, then changing something about the way your neural network works for that sake is not a good idea. Yeah, so I don't have a great answer. I think that that's a vulnerability of work in this space, but we're hoping that experimentation, like what we did, is helpful for the conversation. Maybe even the conclusion is don't use this loss, right? Maybe somebody goes out and trains this thing and gets consensus in a way they didn't want, and then they have an idea that this is not a good idea for them. But hopefully they can have that conversation with these results.
And just one last question. So how do you sort of compare this with, let's say, an alternative approach, which is, let's say you pick some sort of a evaluation metric where, you take the top K features, you sort of perturb everything else, and then you see how much the prediction changes. And, let's say you run Lime, Shap, all the gradient-based approaches, and then you pick the best out of them and say, oh, based on this metric, maybe Lime is giving like the more reliable explanation. So I guess one approach is what you're suggesting, which is, let's train a model that can make these methods disagree. The alternate approach is, how about we do some evaluation on the faithfulness, or with respect to the faithfulness of what these methods are getting, and let's pick the one that is best. And in fact, I had a third point, which is that maybe it's interesting to also see empirically if that faithfulness of the explanations you would get with a vanilla model, how would that compare with like the faithfulness of the explanations you are getting once you use your approach? In the sense that, is your approach also helping you get more reliable explanations, I guess? Like, yeah, that's like, it's a long question, but I think it has a few.
Yeah. Okay, I love the idea of evaluating things after the fact to make decisions. I think that that's a good idea. I think that the particular evaluation scheme where you zero out the bottom,
Yep,
whatever features, runs kind of a big risk, because being in the top K doesn't mean you're the only feature that matters, right? You might have a decision that actually depends on every single feature, and maybe even depends strongly. But if you ask an explainer for the top 5, it's still going to give you a top 5. So I would be a little hesitant to say there's a great evaluation scheme out there, right? It gets back to sort of this ground truth question. It's hard to know, looking at explanations, which is good or which is right. And it's similarly hard to tell which explainers you should be using, even in a particular setting. I think that that's all kind of related. But evaluation after training is a nice thing. I mean, for one, it doesn't require retraining, right? If you have models in deployment and you're trying to understand them, training can be expensive. Maybe you're the type of business that spent a lot of money on the outset training models, and now they're working for you and you like the results, but you're also after explainability. Then something like what we proposed here today is like not useful for you. And so post hoc, maybe I shouldn't say post hoc evaluation, it's like borrowing too many words, but evaluating that model to decide what to do is super useful. Yeah.
Any other questions, thoughts? Okay, I think we're probably good and we're also a bit out of time. So thanks again, Avi, for joining us today and sharing all your work. We'll stay in touch and of course we'll arrange some meetings with other students and so on. Thank you so much.
Sounds great. Thank you. Bye.